yeah, hopefully today will be good, so we can have a meeting with yeah, we can follow the meeting in a full duration. And yeah, for all of the participants that hasn't joined with our Google Classroom, maybe later I will share the link so you can submit your assignment or get the learning materials that Professor Supa sent to me, and I will share it by Google Classroom.
Yes. Yeah.
And now it is already 10, so without any further ado, Prof. Supa, this time is yours.
Yeah. Thank you very much for everything arrangement. And one thing that I have to tell you, Mita, I tried to connect to the classroom, but it couldn't successful. I don't know why, probably my email or something. Sorry for that, but I think we can do it later.
It's okay, Prof. So,
Yeah.
let me know if there is anything that we can prepare for you.
Yes. Okay, so just like to check a little bit. Yes, my sharing. Where is it? This one. I don't know about the feedback of last week. If the student can follow things in details, they can also email if they like. And for today, Selamat pagi, everybody.
Pagi.
So,
Pagi.
yes.
Pagi.
Computational chemistry course that I will give the lecture on molecular mechanics. Continue from last time that we have already introduction about computational chemistry. You may feel the big picture of that and this method and the applications. And today for molecular mechanics method, it is indeed very classical mechanics since 1920 something up to now. Molecular mechanics method still been the very popular methods and applied to all area of research, especially in chemistry. Okay, so we will see about the fundamental on that. And next week, then we can go through ab initio and something high level of calculations. So for today, I'd like to tell you that molecular mechanics, I have to thank Mr. Harvey that he already gave the fundamental thought of molecular mechanics on the 9th of this month already. And so today, I will give you focus on the limitation of the calculations. So I will give some short introduction of force fields for some of you who may miss the first lecture of Mr. Hafiz, okay? And then we can go through the basic theory and some physical meaning or the significance of this method, okay? And also the development of the method up to now. And at the end, I will discuss about the existing force fields. There are several types of force fields and quite enjoyable to see their applications in some material science, in biomolecules, and also in the field of drug design. And I'm sure some of you may be interested in to see its performance, okay? So the first topic that I like to give you again, actually last week I already mentioned on that, but okay, we have to concern about the limitation of computation. For example, the limitation of ab initio method is limited based on the size of the molecules. Okay, so it cannot be applied to large molecules. Okay, and even even the accuracy of the method that I discussed last time, you can see that the limited number of atoms, just 10 or 20. Anyway, I have shown you already that the supercomputer at the moment, it provides the opportunities to enlarge the system of ab initio more or less, but not everybody can access to those supercomputers. It's also high cost of investment, okay? And then I have explored a little bit about semi-empirical calculations that can be used to large organic molecules, but also it takes to computation intensive, especially for biomolecular system. And these provide opportunities for molecular mechanics, okay, to combine with both ab initio or semi-empirical, okay. So in this work, if we have to apply for the larger molecular system like proteins, nucleic acids, or biomolecular molecules, the molecular mechanics method is very important. And you can see that with the size, from the small size to the medium size, and then to the bigger size of the system, we can apply, especially in the field of biology. So this is very important picture that we need to adjust about our system and our method. Okay. So I would like to say that every discipline has its heart, okay, the core concept, or the thing that I would like to say that the key information, okay, for molecular mechanics, force field is that. So if we ask, what is a force field? I like to tell you that a force field is a mathematical expression that describes the dependence of energy of a molecule on the coordinate of atoms in the molecules, okay? So I will go a little bit slow due to I think the wide variety of the participants. Some people, some students might be new in this area, and some students may be a graduate student, maybe they have some knowledge on that, okay? But this is very important. Mathematical expression based on the harmonic oscillator expression, which provide the simple energy function term, but based on its simple energy function term, it can describe the dependence of the molecule's energy on the length of the bond in the molecule, okay? So the force field is based on the intermolecular interactions and intermolecular interactions. You can see that from this structure, this is the second time that I show this picture. It's simple and very important. Two atoms connect by bonding. And if we have another atom, it can have the angle, okay, the angle. And then based on the harmonic oscillator, you can have stretching between 1 and 2, 2 and 3, and then you can have the bending, okay, angular moment over here. So you can have the bonding, and then the angular energy over here. And for the next atom, like atom 4, you can have 2 dihedral angle, and then it can have the oscillator stretching, bending, and torsional energy, okay? And for the long-range interaction terms like atom 1 and atom 4, which both are not connected, okay, to each other, but still they have the interactions between two rigid spheres. And then we have the potential energy that can explain on that. So if you understand this, we can talk about only both part, the whole lecture. And then I will show to you that the second part of the potential energy is very crucial, very important, because many of molecular mechanics softwares and methods, they have been modified this part in order to make its prediction to be precise and can confirm the experimental data. Okay, so this is very important about the intermolecular interactions. Okay, so the basic theory of molecular mechanics or force field. Again, the molecular mechanics energy expression consists of the simple algebraic equation for energy of a compound. The quality of the molecular mechanics depends on the constant in the equation, which the constants obtained from spectroscopic data. And also we can have it from ab initio calculations at the very high level of calculations. So the constant will be selected in order to make the equation and then make the prediction precise, okay? And so the set of the equation overall of this, we call it force field. And you can see that sometimes the fundamental assumption of molecular mechanics method is a transferability of the parameters. Like we look at the atom like atom, ball, and stick, okay? Ball and stick, okay? So sometimes we look the whole picture altogether based on the parameters. So the energy is associated with the particular molecular motion. If you think about the molecule like water molecule, 1 oxygen and 2 hydrogen, okay? They are stretching, bending all the time. And so it can have some motion. And then we can obtain the energy from that. Because of these very simple calculations, but the performance of molecular mechanics then be applied to the large molecular system. This is wonderful. And I would like to say that it's really long history of molecular mechanics, almost 100 years of development of molecular mechanics up to now. Very efficient, simple, but efficient, okay? So then for molecular mechanics of force field, we describe a molecule based on ball and spring, ball and spring harmonic oscillator motion. And these can be representation of equilibrium geometries if you compare to the plastic model like ball and stick connect together to make the structure of the molecule. Plastic model cannot give the equilibrium geometries, but molecular mechanics can make it. And then we can also able to compute the relative strain energies. And I would like to say that up to now, the computation is very cheap based on the investment, on the software, on the hardware, and the CPU time is very fast, okay? So very cheap experiment. Lots of the empirical parameters that are available. And then we can be able to test and calibrate molecular mechanics method. So the limitation of molecular mechanics is that, as I said, it depends on the equilibrium geometries only. And it does not take electronic interactions into account. So we cannot use molecular mechanics to follow about the bond breaking or bond forming or mechanism of action, okay? And also no information on the properties or reactivity. And these are the limited of molecular mechanics. So you have to take care when you use molecular mechanics. It's simple and good for some particular system And it's very good when we combine molecular mechanics with quantum mechanics, which I will talk about this in the next probably 1 or 2 lectures. So when we use molecular mechanics of force field, the performance of force field technique is dependent on 4 factors. These are the criteria. The first one is that the function form of the energy expression, okay, the equation of molecular mechanics. We have the standard form, but we can modify the interatomic interactions form, okay? And then we can generate so many molecular mechanics function. I will show to you later. And the second is that the data that used to parameterize the constants is very important. If we parameterize the constant in the equation obtained from experimental data, that would be very good. And if not possible, we can get it from ab initio calculations. So it depends on the data that we use it to make the constant, okay? And the next is that the technique that we use to optimize the constant. So if you use some fitting equation, very good linear relation equation fit well like this, you can obtain the good constant, okay? So it depends on the data and the technique. And the next is the ability of the user to apply this technique in the way that consistent with its strength and weakness, okay? So the user like us, we are chemists. We would like to do some experiment in the lab, but at the same time, we would like to predict the properties of the molecules based on computer modeling. So we have to have some awareness on those methods. Every method, computational method, there are limitations. We need to know about the strength, and also we need to know about the weakness of the method. And if we can use that in the correct way, correct and suitable system, it's fine, okay? This is the way that I would like to mention at the first step. So now come to the energy expression, which is the heart of force field. The energy expression, Mr. Hafiz mentioned once already about how to obtain the molecular mechanic energy, okay? It comes from intermolecular interactions, which based on harmonic terms, harmonic oscillator term only. Intramolecular interaction, bonding, bending, and torsion energy, okay, harmonic terms. But for the intermolecular interactions, the energy comes from the Coulomb term, which based on atomic charges, and the equation as very well known and famous equation, Lennard-Jones 612 potential. So if we look at the energy expression, it is a mathematical terms combined together. The first one is the bonding energy, bending energy, torsional energy, and Coulomb energy. And the last is the Lennard-Jones potential. So you can see that when we sum over all these simple classical equations, we have the stretching, bending, torsional, electrostatic interactions, and van der Waals force. And sometimes we can add to the last part, we can add some other forms. For example, hydrogen bonding, which I will show you later. The quality of molecular mechanics is based on the last term because the first 3 terms are really fixed, okay? And the charge of the atom are also fixed, but the intermolecular interaction, the last term, we can do a lot to improve the quality of the force field. Okay, so the force field can say that it will differ. There are so many force field types, and it will differ on the number of terms in the energy expression, as I said. Okay, and the limitation is that electrons are not explicitly included. So electronic process cannot model, right? This is a limitation, the first limitation. So when we look on the bonding, stretching, and bond angle, as I said, described by harmonic oscillator equation, which is approximation. For the bond stretching, you can see the Taylor series expansion around the equilibrium bond length. When I said like this, some student may have no idea about what is it. So just look in the oscillator. In the oscillator, when you have stretching, the two atoms in and out, and then there will be a equilibrium distance between. Okay, the equilibrium distance is the B0. And then we subtract it from the bonding between two atoms, then you can have the value over here, and you can have the force constant. The constant over here, we call it force constant based on bond stretching. Okay, for example, if we have the chemical type like CC single bond, CC double bond, and CC triple bond, you may imagine the stretching of CC, okay, not so hard force, but for C double bond C, okay, the force is higher. The most is that the C triple bond, the force constant is the highest, okay. So this is the feeling that force constant can represent the structure and can represent their properties, structure and properties relationship. Okay, and you can see that C single bond C, you can have bond equilibrium of about 1.5 angstrom, and for double bond 1.3, and C triple bond 1.2. Okay, so these are the equilibrium stretching of the CC chemical types. So you can understand right now about its physical meaning, okay, and how to get it. The force constant can obtain from experimental data. As I said, they have so many try to construct the equation and the prediction, and then at the end they can obtain the force constant, right? KB over here. And for the prediction of the bond energy, when we have the equation, we can predict the bond energy, okay, of the triple bond, double bond, and the single bond, like this. You can see that this is a shape of harmonic oscillator, okay. And in this way, you can see the force constant of the C triple bond is the highest. And it can locate it to the bond length 1.2 and 1.3 for double bond and 1.5 for single bond. Okay, so I think this is very nice, and I obtained from the slide of Karin from CNRS, very nice, and I make the credit to her. For the second term, Taylor series expansion about the theta zero over here. So you can get the angle energy or bond angle energy, okay, from the same summation of the force constant, and then you subtract the theta over here, theta, and subtract by equilibrium theta. The same, you can sum over all here and get the bond angle energy. Yeah, this is very nice to repeat this. And for the torsional potentials, we have the Taylor series of the cosine function. You can have the force constant over here and the 1 plus cosine term. And for this, you can see the energy. If you plot about the prediction of the energy due to the torsion angle and the stagger conformation of some single bond represented in some molecules, you can see the cosine curve. And at the bottom, these are the torsional angle. Stagger conformation would be more stable than eclipse conformation. And the same is true if we apply to some organic molecules like 1,2-dichloroethane. Everybody know about 1,2-dichloroethane, right? Very simple molecules. And what you can have is that if the dichloro, they are on the eclipse conformation, the steric interaction between the two groups make the energy high and not stable. But it would be more happy to be staggered over here, like about 60 degree, and very happy to be like a trans-dichloroethane. Okay, you can see that the energy over here is very low and is the most stable state of this 1,2-dichloroethane. Okay, so we can say that the gauge at the 60, 180, and also 300 are the conformation of the isomer that the stability of the molecule very happy on that, but for the eclipse, they are not happy. It's not stable. They have to come down to the valley of the energy like this. Okay, this is quite nice and make you more visibility of the torsional potentials of the molecules by molecular mechanics based on this simple equation. Also, there are some improper torsion occur, especially when we consider some molecules like peptidic bonds, peptides, peptidic bonds, and there are some part of the molecules that out of plane. Okay, they are out of the planar plane, and then this angle will show the improper movement. Okay, this is quite important when we apply molecular mechanics to the biomolecular system. We have to concern that. So we need to consider about the torsional energy terms. And then for the intermolecular interactions that I introduced to you, the van der Waals interaction is very important. And from the long history of our knowledge, one of the most common methods for describe van der Waals interactions between atom I and atom J is the Lennard-Jones potentials. We call it Lennard-Jones 12-6 potential. So if you look at this equation, Lennard-Jones 6-12 potential, there are two terms. The Lennard-Jones potential equal to 4 epsilon, and the first term qualitatively gives the electron exchange repulsions. And the second term is the long range representing the attractive dispersion interaction. Okay, so when we consider the diatomic parameters, we can apply to this simple picture of the Lennard-Jones potential. You can see that when the two atoms very far away, there is no interaction at all, but when we come closer and closer, you can have some repulsive interaction that steeply increasing. And also there are some attractive when they close together, okay? And then the energy is lower. That means the system is more stable and happy. But anyway, for the Lennard-Jones potential like this, it is the observed potential results from the balance between the attractive and the repulsive force. So the curve, the black curve over here, we call it Lennard-Jones potential because of the balance between attractive and repulsive. Okay. So when we look at the molecular geometry and molecular properties, you may think about the non-bond interaction term, non-bonded interaction. That means the interaction in that lies over here are the interactions between the two atoms that not connect to each other. Okay, so non-bonded interaction, we can have the energy of the non-bonded, and also we have the electrostatic, which represented by Coulomb energy, summation of Qi Qj over the epsilon and the distance between two atoms. Very simple. Everybody know about this. Okay. So for the van der Waals, I just mentioned to the previous slide from the Lennard-Jones 612 like this, 12-6 term like this. So you can obtain the curve of the potential of the Lennard-Jones potential. But there is another equation that we represent the hydrogen bond interaction. This is the also Lennard-Jones, but in the form of 12 and 10. Okay, you have 12-6 for van der Waals, and for hydrogen bonding, it is a 12 and 10. Okay, so you can see that for intermolecular interactions, we have two key potentials. The first one is van der Waals, and another one is hydrogen bond. So if you add, you have 1, 2, 3, 4 is the electrostatic, 5 is the van der Waals. You can add 6 term hydrogen bond. Okay, and some molecular mechanics development, sometimes they try to put the 7th term, the 8th term into the equation in order to improve the quality or the prediction. Okay, it could be, but sometimes it not help. Yeah, not much help. But for van der Waals and hydrogen, they are already verified in the equation. Okay, so most of the program packages, you will have both terms in the equation of molecular mechanics, right? And if we look, for example, water molecules, we can express the potential energy from very simple. You have 1 oxygen atom and 2 hydrogen atom. You have 2 bonding, B and B prime, and you have the zeta angle between these stretching, okay? So you can express the equation like the first term, bonding and bonding, okay? And the second term is the bond angle potential. Then our duty is that we have to find the force field, the KOH, the B naught of OH, the KHOH, and the zeta naught of the HOH. Okay, these are the parameters of the force fields. So we have to do many of the experiments to obtain the energy of the water molecules, and then we can fit into the equation until at the end we obtain the parameters. Okay, so these are the way that we can consider about how to express the equation, how to obtain the force constant. Okay, so you have to do many experiments and then use the data from the experiment, put into the equation, try to solve the force constant over here. Anyway, this is also very efficient molecular mechanics. When we apply the energy term, like we already consider, to some system like protein and inhibitor interactions. So later, there is one development in molecular interactions And we have the program package called docking, molecular docking. Some of you, I'm sure you have heard about this, and even some of the senior student or academic staff may use docking. It's very simple, okay? And based on the method of molecular docking, the objective is to search for the orientation with low interaction energy. So come to the basic, okay? The basic of molecular mechanics, we have the molecule A and molecule 2. The intermolecular interactions like this will represent the binding of or the interaction energies of the system. So we have this kind of Lennard-Jones and also the potential, Coulomb potential, okay? You can see that from the fundamentals of molecular mechanics can be used their potentials and generate the software or the molecular modeling method like molecular docking, and very efficient. Molecular docking is very efficient, especially nowadays, in order to search for the potential SARS coronavirus protease inhibitors, okay? Docking can search and screen some potential compounds in order to develop for the anti-coronavirus, for example, main protease inhibitor, right? This is very interesting, and you can see I really happy when I look at the molecular mechanics and its applications never die. It's still existing, it's still efficient, okay, and very applicable to solve the real world problem. This is a message that I would like to emphasize. And for the electrostatic interaction with represented by the Coulomb law, you can see that it is just the electrostatic. It is like a charge that normally we obtain from the non-orbital based algorithm, which is designed for molecular mechanics. So the partial charge will be on the nuclei, nothing concerned with the electron. If we talk electron, we have to wait till next week to study about basis set and also ab initio, okay? So in molecular mechanics, we use only the partial charge on the nuclei like this, partial charge on the nuclei. Anyway, it can be described best by using atom types, which is parameterized for describing charge center. I mean the parameters of the atomic charge. For example, we need to parameterize for oxygen atom, which is different from carbon atom. Okay, this is the meaning that I would like to emphasize. And sometimes the dielectric constant can be included in order to model the solvation effect. Okay, this is very helpful indeed, especially for the solution. You may think about chemistry is the change of matter which occur in the solution. Okay, so we need something that represents a solvent effect, and dielectric constant is that. And I like to give you some common force field term, right? For mathematical forms which expressed in the energy terms, as I said, the constant, very important, and it can vary from one force field to another force field according to the designer's choice of the unit system, the zero of energy, and the fitting procedure. This is a way that molecular mechanics have been developed from time to time, better and better, and very precise to predict the real properties of the system. And you may remember that the constant come from experimental data or an ab initio calculations. Okay. Most of the molecular mechanic method up to now, they have been developed and they have been parameterized against specific class of the molecules, which I show you later. Okay. For example, molecular mechanics, parameterization for the protein system, for the nucleotides, for the wide variety of organic compounds. Okay, they are different. They need the specific constant to precise the experimental data. Okay, and sometimes force field method have been parameterized for all elements, but very few. Yeah, it is not easy to predict for all elements. And for this table, you can see that for the harmonic represent the bond stretching and angle bending, and the cosine represent the torsion. Energy term is like here, as you have already seen. And the Lennard-Jones 612 represent van der Waals. Sorry. And also Lennard-Jones 1012 represent van der Waals. You can see that. You can see that. 1012 van der Waals and hydrogen bonding. If you like. Yeah, somebody sing a song. Yeah, right. Good. Okay. And for the Coulomb, you have the electrostatic, right? And I like to tell you that sometimes there are some cross term, you know. Cross term means we cross term between stretching and bending. Okay. And we can have some term like this, cross between stretching and bending. And also the name of the function like MOS can be the bond stretching, which is represented by this term 1 minus e exponential of the minus alpha something. Okay, so there are so many terms that we can include it in the force field equation. And so then for the general force field calculations, because you will have a chance to play with the molecular mechanics in the laboratory, the computational laboratory, molecular modeling after the midterm. So very simple that you just try to construct the input. You have to select the atom types. You have to construct the starting geometry and make the atom to connect to each other, how to connect, right? And the next, you can calculate energy minimization with the program package. We'll do it for you, and you can obtain the geometry that already very stable, or we call it optimized structure. And at the end, you can calculate molecular properties after you obtain the geometry, okay? And finally, you can have molecular structure, molecular energy, and some properties. For example, you can have the dipole moments, which is quite important for chemical structure. And in this slide, it is like a force field atom type. In molecular mechanics, atom given type, there are several types of each atom. For example, you can have carbon atom, nitrogen, oxygen, hydrogen, hybridization like sp3, sp2, sp, and environment like you have cyclopropane or cyclobutane. So atom type over here, the first case, you can see that with the A18, ethene, and carbonyl group, atom type is different. Okay, so you can define like type 2 carbon atom or type 3 carbon atom. Okay, and for some molecules, we can use the transferability and assume that, for example, the carbonyl bond will behave more or less the same as all molecules. So this is the meaning of the transferability. So this is a little bit detailed, but just give you some insight about atom types. There are so many things, okay, different to each other. And I like to talk to you about the basic theory of the molecular mechanics. The physical meaning, you know about the equation, okay? You know about how to express the equation. And after you obtain the equation, then you try to construct the atoms and try to predict or calculate the properties, right? You have to take care about the force field because of its simplicity, okay? And the complexity calculations will be done because they omit most of the hydrogen atoms, okay? And the parameter describing each backbone atom are modified to describe the behavior of the atoms with the attached hydrogen. For example, if we use CH2 group, right? We use CH2 group rather than specify sp3 carbon bond to the hydrogen atom. This is a transferability. That means it's not different much. And later on, we call it united atom force field or intrinsic hydrogen methods. Most often employed to describe very large biomolecules. This is very efficient, okay? And if we have computer hardware available, then we can use the more accurate explicit hydrogen force fields, okay? Explicit hydrogen force field, that means you have the parameter for hydrogen atoms to be included in the interaction, in the calculations. And some force fields later on, right now, there are atom types for use with both implicit and explicit hydrogens, right? So I like to give to you a little bit more information that the force field parameters, very important, the parameters, the force constant, the equation. The base is that we should obtain the parameter from the original data. I mean, obtain from the experimental data, right? UV absorption or energy, or the base is that ab initio calculations, the high level. If we get that parameter, that is the base, okay? And the bond stretching and bending are relatively stiff motions which can describe very well by using equilibrium values. For example, the values obtained from X-ray diffraction results and the force constants, because the force constant means the harmonic oscillator, okay, motion. Then we can obtain it from vibrational spectroscopy, okay, like IR spectroscopy. For the torsional behavior, it is sensitive to both the torsional of the isolated bond and the non-bonded interactions between the distant section of the molecules or the surrounding of the molecules. Therefore, the choice of fitting fossier become important because it determines how much energy is from contributing process, okay? That means torsion energy is not easy to obtain, okay? So we need the fitting equation to make the prediction of the force constant very efficient or very precise. And at the end, the force field can also parameterize to the base predict of the vibrational motion or the intermolecular force. If you remember, modeling computer calculations is the predict of the reality. That means our method, if our method is good, we can predict the real world. Okay. If not, we have to come back and try to improve our method. This is also the way we use the experimental data to be benchmarking, to be the reference value, and see if our parameters is good enough to predict the real properties of the molecules. Okay. For example, X-ray diffraction or vibrational spectroscopy, then we happy with the force field. So I would like to go a little bit further for 1 or 2 slides about what we obtain from molecular mechanics. We obtain the conformation energies. If you imagine, we have equation, we have molecules, we have parameters, and then we calculate, we predict the conformation to get the good geometries. And then we can predict for the base properties from the equation. So the energy computed by molecular mechanics are usually conformational energies. And it reliably predicts the difference in energy from one conformation to the next. Okay. The actual value of the conformation energy does not necessarily to the physical meaning and is not comparable between the different force fields. Okay. Just relative, not absolute value, just relative. We can compare that. And the molecular mechanics method can be modified to compute also the heat of formation, but we need a database or the computation scheme to yield the bond energies that might be addressed, that might be added to the conformational energy and account for the zero of energy. Okay, so it's not easy to understand, but I just like to mention that molecular mechanics also can be able to predict the heat of formation, but we need the database, okay, of the bond energy of several of the molecules. Yeah, and then we can predict for the heat of formation. It's quite nice to play around about this. Then, example of the butane. If we have the structure, very simple butane, you have the carbon atom, 4 carbon atom and connect with the hydrogen atoms. And then you can change the structure of the butane. Okay, you can imagine that when we make the bond, the torsional of the butane, okay, to be 0, the energy is very high, about 20 kJ per mole. Okay, and when we twist it, yeah, to be some kind of 60 degree, the energy lower, and then come to higher eclipse, and then come to the most stable geometry, which is the trans conformation. You can see that this is the potential energy. Okay, potential energy of the butane from 0 to different conformation, and at the end it comes to the same point of one cycle like this. Okay, it's nice to see the potential energy of the butane. So the all 9 torsional interactions around the central CC bond should be considered for an appropriate reproduction of the torsional barriers. So we can do a lot about the type of the CCCC bond and the type of the CCCH and the type of the HCCCH. Okay, and these are the constant in the equation that used for predict of the molecular energy of this structure. This is an example, make you a little bit insight into how the equation can predict the molecular properties, predict the conformation energy Okay, and at the end, we obtain the energy profile or the energy potential plot into one diagram like this. Okay. So I think we come to the first part of the lecture. Before I going to another part, probably some of you may have some question or comment. You can send to the chat or you can ask. But during this time, I think we can have a break. How do you think, Mita?
Oh, sure, we can have a break.
Yes.
For 5 minutes. Is
Yes.
it enough?
Okay, that would be fine. Yeah.
And for all the and all for all of the participants, you can ask your questions using chat room since we have 5-minute breaks.
Yes, thank you very much. Yeah.
You, Prof.
So I will stop the share and then we can come back 5 minutes. Thank you.
Okay, thank you, Prof. Okay, for all of the participants, we are going to start our lecture again in a few minutes. So if you have any questions regarding the molecular mechanics, you can simply write it on the chat box.
Hi. Welcome
Hi,
back.
Prof.
Okay, so then we can continue a little bit to the
Yeah,
next.
sure.
To the next.
Sure, Prof.
Yeah, this one. The second part of molecular mechanics, I will show to you about the progression in molecular mechanics and it efficient. This is very efficient method to apply to several materials, biomolecular system, and drug design, okay, based on the existing force field. Very, very nice. So I hope that I can introduce something to you for your interest, and some of the students, probably senior student or graduate student, may have a chance to play with the molecular mechanics. Okay. So this slide, actually, I talked last time about the history since 1930 up to 1990. Okay, with the commercial distribution of the program packages have been extremely productive. And after the year 2000, more and more publications about classical molecular dynamic simulation have been produced, and many codes, many generation of force fields were developed, and very interesting increasing of publications up to now. And I asked my student to search a little bit if we use the keyword molecular mechanics, and then to the Scopus database, you can see that the first publication of this molecular mechanics was introduced in 1927. And not much work published from time to time. You can see that about 40 or 30 years that not much progression. But after the 1966, many of the publications on molecular mechanics, and you can see that about 1990, with the high performance of computers, there are several of method force field were developed. And in the year 2000, many of program package produced commercially, okay, and provide opportunities for research and extremely high of publication each year. That means this method is very efficient and very acceptable. Okay, it's simple and acceptable. Anyway, it needs to work together with semi-empirical, ab initio, and DFT in order to apply to many several chemical systems, not only molecular mechanics, okay? But just give you the feeling of this method. Up to now, so many things and come out. And also the countries that produce a lot of publications on molecular mechanics. We have United States, China, Germany, UK, Japan, France, and also in Asia, Singapore, quite nice, Thailand, Malay, also Indonesia, Philippines. I think we can do it more and more. Good. And so force field were developed from time to time. And you can see that what have been done. If you remember, the potential energy come from mathematical expression, right? And the improvement is therefore try to modify the potential energy function, which can increase the accuracy of the force field calculations. If you remember, the equation predict the properties, and we need to validate with the experimental data. Okay, and therefore, if which force field can predict well, then it is acceptable. Okay, this is a way that force field have been widely developed from many researchers and companies and apply to work to the real system. Okay, so in this way, the force field have been used and be expanded to the range, many range of applications. For example, if we look, the conformational energy is calculated from molecular mechanics for on the organic molecules. We will obtain the accuracy in the range of 1 to 2 kcal per mole, which is good. 1 kcal per mole, that is acceptable. And for the peptides, the accuracy can be a little bit wide range from 1 to 5 kcal per mole, because peptides very complicated system and not easy to predict. Anyway, in some case, it's quite nice. And very rare case that, for example, the weakly bound dimers or molecular complexes, sometimes we cannot reproduce or the precise prediction. There are some error over that. Okay, this is a limitation. But anyway, in general, molecular mechanics commonly use force fields. We have known it via this term MM followed by the number. Okay, MM1, MM2, MM3, MM4, for example. And I would like to say that the MMN, it is known to be the gold standard for force fields, the gold standard, not just standard, but gold. That means very good. Okay. And the parametrization to fit the values come from the electron diffraction, mostly come from X-ray diffraction. And for the bond stretching, is represented by the Hooke's law expression, like explained in this equation, right? Here is the Hooke law harmonic oscillator, which we know already, and also the Taylor expansion of the term. This is very fantastic mathematical method, Taylor expansion. Okay, very efficient in order to solve some equation in quantum mechanics and also molecular mechanics. And we have the MM2, which can be unstable, and later on it was developed to be MM3. And for the MM3, the development of molecular mechanics MM3, there are 153 atom types for organics and biomolecules. Okay, quite nice, very good. And later, MM4 has been developed, follow from the MM3 in order to use for hydrocarbons, alcohols, ethers, and carbohydrates. It is important to note that MM2 and MM3 are the force field in the Chem3D. It is the name of the program package. Okay, and MM2 star and MM3 star is installed in the macro model, also the name of the program package. This is just the information to tell you that molecular mechanics have been always developed into better and better. Okay, and then the software package, they have developed the software package, and then they can sell, they can commercialize, and quite good business. Okay, the company that construct the molecular modeling package, they have very good business on that. And the modification may be followed by date, for example, MM3, and in the bracket, it is the 94, that means the year of this term, this is molecular mechanics, was launched out. So I will introduce to you about different type of force field. This different type of force field, okay? And the existing force field in molecular mechanics, which were applied to materials, biomolecules, and drug design. In the first part, I show to you the structure of butane. Very simple organic molecules, right? And molecular mechanics can do very well on that common organic compound. But for the complicated structure like nucleic acid, you can see that not easy, right? There are so many atom type. There might be some charge. There might be some rotation. There might be some vibration. There might be some interactions. There might be some solvent effect along the simulations. So in this way, the first force field that I would like to introduce to you is amber. Amber is very, very efficient, very good, especially in the biomolecular system. And amber is the abbreviation from assisted model building with energy refinement. Okay, so in short, amber. And it is named both force field type and molecular mechanics program. It is commercial. If you like to use amber, we have to pay, we have to buy the license. For example, the university can buy like academic license, not expensive for academic, but for a company or something, it quite be expensive. Okay, so we can use amber for good prediction, because amber is very well parameterized. Especially it has been developed for the proteins and the nucleic acid. Anyway, the amber used only 5 bonding and non-bonding terms, along with the sophisticated electrostatic treatment. Okay, so amber force field is very famous, just 5 terms and no cross term. The name cross term means you can have the stretch and bending term or bond bending term. Many complicated expression included in the mathematical model. Okay, but amber, no, not need to take anything complicated. And the results are very good for protein and nucleic acids, but can be somewhat erratic for other systems. So user, the chemist who use amber, you have to know that you cannot apply amber for other systems of complicated system, but very good for protein and nucleic acid. The second force field that I would like to introduce to you is charm, also very famous. And one of the professor that developed charm, he obtained a Nobel Prize I introduced to you last time, right? You remember Professor Kaplas and some other scientists, professors that also share the Nobel Prize. And charm come from chemistry at Harvard, macromolecular mechanics, CHARMM. So also it is the name of the force field method and also the program package were incorporating this force field. For the academic version of this program, it is designed to be charm, big M, big double M. But for the commercial version, it's called charm. The last M will be the smaller character, okay? And you can purchase for sure charm. It's not expensive, but if you are a commercial company, you have to buy commercial version, quite expensive. It's very, very good. I use both amber and also charm, okay? But it takes quite computing facilities, yeah, because so details in calculations, but the efficiency is very good. If you use amber and charm and you publish some work, then you can have very good results, okay? It was originally devised for proteins and nucleic acid, and based on charm, the very challenging of charm is that it can be applied to many range of biomolecules, molecular dynamic simulation, solvation, crystal package, vibrational analysis, and also QMMM studies. This is fantastic for charm. I and my student also working on charm based on the QMMM study. Yeah. And charm force field use 5 valence terms, and one of which is an electrostatic term, okay? Also very standard term. And here is the example of the QMMM study on the HIV-1 reverse transcriptase that we can focus on enzymatic reaction. So we have to model the system based on the DTTP structure, the aspartate and tyrosine, and also methionine and aspartate around the catalytic site. Okay, very nice, but very tough work, I would say. But if you are interested in it, is something that quite nice to work on enzymatic reaction, right? And charm is the best, I would say. Other methods can also apply, okay, but for the parametrization of charm is very good for protein and nucleic acid. Another existing force field that I would like to introduce to you is the CFF, which is the consistent force field. This force field was developed to yield the consistent accuracy of results for conformations, vibrational spectra, strain energy, and vibrational enthalpy of proteins. And there are several variations of this, such as UBCFF or CVFF or Linji CFF. Okay, you can see that there are so many CFF come out. And if you apply quantum mechanically parameterized force field, QMFF, this is also very good. And the parameterization come from ab initio calculations. Some other thing from CFF is 93. This is the, I guess that program package launched out in the year 1993. And it rescaling of the QMFF to reproduce experimental results. And the force fields use 5 to 6 valence terms, one of which is an electrostatic term, and 4 to 6 are the cross term. Okay, so this is a little bit improvement. And the next force field is CHEAT or CHEAT, come from carbohydrate, hydroxyl represented by external atoms. You can see that we cannot use general force field for carbohydrate because it may be not precise in the prediction properties. Therefore, this force field, the sheet, has been developed, and especially in order to model for the carbohydrate. And the next is the drying. Some of you, if you work on computer modeling, you will see, or you may hear about the drying. This is the force field that we call it all-purpose organic or bioorganic molecule force fields, because it can apply to quite nice organic and bioorganic molecular system. It uses 5 valence atoms, one of which is an electrostatic term. The use of drying has been winding with the introduction of improved method. Okay, it's quite famous. It's quite famous for drying. And the next, I bring you to a little bit complicated system. The ECEPP come from Empirical Confirmation Energy Program for Peptides, ECEPP. This is the name for both computer program and the force field implemented in this program, ECEPP. And it is the one of the earlier peptide force fields that has seen less use with the introduction of improved methods. It used 3 valence terms and are fixed, van der Waals terms and an electrostatic term. Okay, so if you look on the right hand side, these are the peptides that there are so many complicated. There are N atom and also charges on the nitrogen atoms, and also there are the plane of the peptides. Maybe they make some torsion angle. Okay, and the interaction between the two parts, you can see that charge interaction, CN double bond character have been parameterized in the amide or the peptide bonds. So this is very complicated system, and therefore the force field need to be parameterized to make the prediction precise for this system. Okay. And if I give you a little bit more existing force field like EFF, empirical force field, this is also the force field that designed for just modeling of the hydrocarbons, just hydrocarbon only. It used 3 valence term, not complicated, even no electrostatic term and 5 cross term. You see, no electrostatic term, but they add the cross term instead. Yeah? This is quite interesting. And the next, this is quite famous force field. It's called GROMOS. GROMOS come from growing molecular simulation. In short, GROMOS. It's also the name of both force field, GROMOS force field, and the program package. Okay. And the GROMOS force field is quite popular for predicting the dynamical motion of molecules and bulk liquids. You can see on the right hand side, like biomolecular molecules, very big structure, but it is modeled in the liquid, in the box. Your system need to set up the box size. For example, this is the cubic, and put the protein structure inside. And then we need to put the water molecules in order to represent the real world. You may imagine about the real world. In the solution, you have the protein structure you have water molecules, you have temperature, you have pressure in the system, and you have very dilute of concentration. Okay, because in our biological system, the concentration is very, very, very low. Okay, reality we cannot perform, but in simulation, in the modeling, we can perform this modeling to represent the real world. And the use of 5 valence term, and one of which electrostatic, still you can see that force field still maintain the 5 valence term and electrostatic. Okay, but detail of parametrization is different for each force field. And I like to give a little bit mention again about the MM type, which is the gold standard of molecular mechanics. MM1, MM2, MM3, and MM4 are general purpose organic force field, very famous to the organic chemist. There have been many variants of the original method, particularly MM2. For MM1 itself, it's very seldom used, since the newer version show measurable improvements. Okay, this is the way of the molecular mechanics have been developed from generation to generation, and the new generation or the latest version of the molecular mechanics would be better than the former one. This is simple. Okay, and for the MM method is probably one of the most accurate ways of modeling hydrocarbons. It's very acceptable, MM3, widely used among the computational researchers. Okay. For MM4, they are trying to develop to allow the broad generalization about the results. However, the initial published results are encouraging, and there are some, I would like to say that they are not much improved from previous molecular mechanics. So MM4 is fine, but the very famous one is MM3. And there are also the MMX and MM+, which are variations on the MM2. The force field still use 5 to 6 variant terms and electrostatic term, and 1 to 9 cross term. You can see that the cross term, that means the modification of the type mathematic expression on the intermolecular interactions. There are so many terms to be included. That's nice. So for the organic molecules, you can see that very simple carbon, nitrogen, oxygen, and structure like this. So not much complicated. Therefore, MM3 is quite prediction quite accurate and acceptable. May I go a little bit more about the MM? Then you can see more complication of the system. So you need different type of force fields, like MMFF, like here. It is the Merck molecular force field, which is one of the more recently published force fields in the literature. And it is general purpose method, and very popular to organic molecules, MMFF, I would say. And for the year 1994, it launched out this force field, MMFF 94, intended for molecular dynamic simulation. And anyway, this is very famous for MD simulation, and still five valence term and electrostatic term and 1 cross term. Okay. MD simulation use MMFF. So if any of you would like to play with molecular dynamic simulation, you can select which force field is suitable for your system, And MMFF is one of the very famous, right? The next is the MOMEC, MOMEC. Yeah. This force field has been developed in order to describe the transition metal coordination. So the system is more complicated. It was actually originally parameterized to use 4 valence atom, but not electrostatic term. And for the metal ligand interactions, consists of bond stretch term only. This is the cross term, bond stretch. And the coordination sphere is maintained by non-bonded interactions between the ligands. So the MOMEC is generally work very well for octahedron coordinated compounds. And the picture on the right-hand side, just some system that give you imagine of the complex of the metal and the organic system, and sometimes there are water molecules, and sometimes if we need high accurate method, we may apply molecular mechanics with quantum mechanics, right? This is also interesting. For chemical system, almost 1 or 2 or 3 terms of force field that I would like to introduce to you. The OPLS. This one also very famous, OPLS. Yeah? Because the OPLS come from optimized potentials for liquid simulations. You see that for liquid simulations. Only very specific system and designed for modeling of bulk liquids. Bulk liquids, that means the system that you have the liquids, okay, water molecules or something. And it has seen significant use in modeling of molecular dynamic simulation of the biomolecules. Okay, so OPLS also use 5 valence term and electrostatic term, but no cross term. Quite simple, but efficient, specific to the bulk liquids. Okay. So the force field that I would like to give to you, one of an example, a very famous one is TRIPOS. Okay, TRIPOS is a force field created by TRIPOS company, and this force field include in the software namely Alchemy and the CBuild programs, and sometimes it's called CBuild force field. This is the commercial package, quite expensive, but very good for drug design. I also use CBuild package, program package, when I work on the drug design, the discovery of and drug design of some particular system. Yeah, quite nice. And TRIPOS is designed for modeling of the organic and bioorganic molecules. And also this program package generates the application on the comparative of molecular field analysis or COMFA, and use the 3D QSAR technique. Okay, this the picture on the right hand side show to you about the reference compound in the middle, and then prediction of the steric interaction represented by green, and electrostatic interaction represented by red color contour. So when you like to design the new structure that provide a better inhibition, you may add the steric hindrance group over here, or you can add electrostatic group representation over here. Okay, and this suggestion can give to the organic chemists for them to synthesize the new compound and go to the biological testing. Okay, this is the way of the drug design, and CBuild program is very good on that. 5 term and electrostatic. Okay, Another example about the existing force field is the UFF. UFF is the stand for universal force field. So the name universal force field that you mean, I mean, is very, very, very good. They include all elements, and I would say that universal force field is very applicable to general system and very good. Yeah, include all elements. This is a performance of this force field, and also this is the most promising full periodic table force field available at this time. Very famous. Yes, and most widely used for the system containing inorganic elements. Okay, so if you are a material scientist and you would like to model the material of your system, probably come from many types of inorganic elements, the UFF is the choice, the good choice for you to model. Okay, and it was designed to use 4 valence term, but not include electrostatic term. Okay, this is because UFF was designed to be used without an electrostatic term. In the literature, when we search for the information about the UFF application, one piece of the software recommend to use the chart obtained with the equilibrate method, right? And this kind of research can guide us how to apply UFF into some particular system in order to get the accuracy of the results and get the better without the charge. So you can see that this is just an example to give to you that we may have the inorganic elements in the cluster of organic ligands or something like this. So if you like to play with this kind of system, the UFF can be a good force field for you. Okay, just select the system, the appropriate force field, and then do the calculations. Finally, the last one, YETI, Y-E-T-I. It is the name of the force field, which is designed for accurate representation of non-bonded interactions. It is often used for modeling interactions between biomolecules and small substrate molecules. It is not designed for molecular geometry optimization. So when you like to optimize the molecule, you need the force field like amber, and then YETI can model later about the process. Okay, and the application of YETI is to support for the metals and the solvent effect. So you can see from the right hand side, if you are interested in like system like this, you have some metal in the system and surrounded by the solvent. Okay, so the inner part we need to apply by quantum chemical calculations, but the rest of the system, that including water molecules like this, we can apply by using the molecular mechanics force field, and we can understand what happened. Okay, this is the way that molecular mechanics can work well with quantum mechanics. Only molecular mechanics itself, it can apply well to biomolecular system, but for inorganic elements or interaction of metal something, you need quantum mechanics for such a system. Okay, so for the company software, I have introduced to you last time that there are so many softwares, and the company that develop this kind of software, they are still existing, and some may be stop their business. But the application of the molecular mechanics in material discovery or drug design and research, very, very active, I would say, especially at present and also in the future. Okay. So at the end, I think I have introduced to you about the concept of the force fields, which is the heart of molecular mechanics, and how to deal with using the molecular mechanics. You have to think about your system first, and then if you are just organic molecules, you can use type force field. If you are biomolecular scientist, you have biomolecular system like protein or nucleic acid, you may use some kind of force field like amber, gromec. Okay. And if you like to use the simulation like molecular dynamics simulation, you may select force field like gromos. Okay. Or if you are interested in drug design, you would like to design some good structure for develop drug, you may select a tripose force field and many more. If you are material science, you need to use the UFF. Okay, there are all atoms available in the force field. But if you are really material scientist, you may need to use with other method like quantum mechanics. You may have to use the combined method between the quantum mechanics and molecular mechanics. Okay, so as a chemist, we need to understand the method. We need to know our system, and we need to select the appropriate method to model our work or our study. And finally, at the end, we can understand the molecular properties and see what happened, or design something new, or develop of the materials. Okay. So for the take-home message, I think very simple. You may ask yourself, what is force fields? I expect that you may express mathematical expression at least 5 terms, okay, including 5 terms and the electrostatic term. If you can express that fine, very fine. More importantly, I do hope that you may pick up some examples for the existing force field and can explore a little bit about its application. Okay, material science, biomolecules, or drug design. Okay, that's fine for me. If you are able to respond this take-home message for yourself, you can read many more. So many things on the available in the cloud, in the Google, and also many of the video lectures that can make you more understanding about the molecular mechanics. And I really happy to give the credit to all the materials that I have used for the lectures, and thank for them. And hope that next week we can go into the high level of calculation. In 3 weeks next, we will talk about ab initio. Okay, but we will start based on the basis set, which is the heart of ab initio. Okay, the basis set, the heart of ab initio. For molecular mechanics, the heart is force field. Okay, so you need to know the heart of each method, right? I have seen any question from the floor?
Yeah, I see a questions from Anissa Rizky, Prof. There is several existing force fields that's suitable for same molecules. For instance, either amber or charm are suitable for proteins. What are consideration in choosing one of them?
Yes. For example, if you work with proteins structure, MD simulations of this kind of biomolecules, you may use amber or charm, no problem. But you need to have high performance computers, because both program package, they quite use computer times. It take a long time, take quite CPU time, and also the facilities like the hard disk and the efficiency of the calculations. Okay, both really good program package for biomolecules. If you have computer, high performance computer, you can use amber and charms, but both are also commercial package. If you can purchase license, no problem, just do it. From my experience, amber is more friendly user, but for charm, quite complicated, not easy. For charm, I have an experience to work on the enzymatic reaction of HIV-1 reverse transcriptase, as I mentioned earlier. And my PhD student used charm to produce the enzymatic reaction, the QMM simulation, and to find the energy potential surface. It took a lot of CPU times, really, and quite complicated. Okay. So if you ask me what are considerations in choosing one of them, the first one is the objective of your work. Okay. If you would like to just do MD simulations, you can use amber. It's more easy. Okay. No, not more easy. It's more friendly. But if you would like to do enzymatic reaction, okay, I recommend you to use charm, but tough and more complicated. First, research topic. Second, infrastructure. If you have facilities, just do it. Not easy. Amber you can use from PC, charm. I think right now you can perform charm in the high performance computers. It's quite cheap. I mean, computer rather cheap right now, so provide opportunities to play with the charm. Yes. Thank you.
Okay, thank you, Prof. Supa, for the answer. Anissa, hopefully it is meet your questions. So yeah, because the times is up, I guess we have to end our meeting. So it is very nice topics in molecular mechanics, since it can help us to to do the calculations more efficient. Sometimes I use molecular mechanics to optimize my structure before I calculate with higher quality of calculations, such as using DFT or ab initio calculations.
Yes.
It is so helpful, Prof.
Yes.
And yeah, for all of the participants, maybe you can also use the molecular mechanics. For instance, we use in Avogadro, we can use UFF molecular mechanics, and
yes,
it is quite good to get the optimized structure.
Yes.
And yeah, for all of the participants, we thank you very much for your attendance, and also Prof. Supa, thank you very much for the explanations.
Yes.
And we have sorry, I guess we have.
I have one comment from my experience. For the undergraduate student, I will introduce molecular mechanics for the student to construct the organic molecules to optimize and see the structural parameters like bond length, bond angle, torsion angle, and then some properties like dipole moment or log P. Program package like Hyperchem can be used to model the structure. But I think you have the Avocado, right? Avocado also very good program package. Yeah. So for undergraduate student and senior student in graduate study, I think you may play around about molecular modeling. It gives some hint, understand more and more. And if you like to do research, just go to PhD study. That would be fine. Master degree or PhD. And try to work on that. Mm-hmm.
All right, thank you very much, Prof. So I guess computational chemistry is not only for computational chemists, but also for help so much in learning organic chemistry, such as conformational, energy, and so on. Yeah, it is a good way to help us in understanding chemistry. So for all of the participants, there is an attendance form that you have to fulfill in the chat room, and if you meet some difficulties in joining our Google Classroom, we will invite you by email or Sima here. Yeah, if I'm not mistaken. Yeah, we will invite you by email. So please kindly fulfill the attendance link, and we will meet in next week. Yes. On the same Zoom account.
Yes.
And we also on 10 a.m. Yeah, and the topic of basis sets with Prof. Supa.
Yes.
Okay. So thank you very much, Prof. Supa. Thank you again.
Thank
hope you
all.
are always
Take
in
care.
good health.
Okay, see you next week.
See you next
week,
Prof.
Day.
Supa. Have a good day.
Thank you.
Thank you, Prof.
Very much.
Bye-bye.
Bye. Thank you.
Take care.